So what I will do during class meetings is I have these documents where I actually have my notes from last time, but as I'm going through these, I might want to make changes to them. For example, what if someone asks a question and besides just answering a question here in class, I want to incorporate that answer into these notes. So I could actually edit these on the fly and have these nice readable questions, which are far preferable to my own penmanship if I were to write on the board. So these notes with whatever changes I make during class, I will then post in Canvas. So this class being 2:30 to 3:45, generally by around 6 p.m. or so, I'll finish my post-processing and whatever notes and videos should be up later that day. Okay. Are there any questions about how the class will be run? Okay. All right, so we still have 54 minutes. We'll ease into this. So this class, as I said, is all about partial differential equations, also known as PDEs. So I'll be using an abbreviation throughout because I don't like writing out partial differential equations. So by now, in Math 285 or whatever first differential equations course you took, you've already seen what are known as ordinary differential equations, or ODEs, and now we move up to PDEs. The distinction between them is very simple to explain. For ordinary differential equations, your solution is a function of only one variable. So your ordinary differential equation involves derivatives of that unknown function, that solution, with respect to that one variable. Generally like a function of x or a function of t for time. Whereas in PDEs, your solution that you're seeking is a function of several variables, like x and y, or x, y, and t. So a function of both space and time. So in that case, you have your equation features partial derivatives of your unknown solution with respect to each of those variables. And what you'll find is that often solution techniques for ODEs are very useful in the solution of PDEs. We tend to, like if a PDE has a solution that depends on, let's say, 3 variables, then we can decompose that PDE into 3 ODEs, one for each variable. In fact, that's the very first solution technique we will learn. It's called separation of variables, reducing a PDE to multiple ODEs, and in the solution of those will be used to build up the solution of the PDE. So we'll be falling back on what you would have learned about how to solve certain ODEs. Now, I have learned to assume that from one math class to the next, that students forget everything. But if it's something they have seen before, if I just take some time to review it, then it comes back to you. So I'm not going to assume that you remember the content of Math 285.
Thank you. It's been almost 4 years for me.
Exactly.
Yeah.
Because for some people it's 1 semester, other people it's been 4 years, or who knows how long. So, the funny thing is, I actually never, as an undergraduate, I never took a course on ODEs. So quick background about me. I got my bachelor's in math and computer science at Purdue University. Back when the first George Bush was president, is when I graduated. And then got my master's and PhD in scientific computing and computational mathematics from Stanford. And I've been at USM since 2009. I'd even taken a class in PDEs, like the equivalent of this class, as an undergraduate. They just let me take it. And then when it got time to graduate, they're like, oh, you never took ODEs? And they're like, fine, let them out. Yeah, whatever. I read Math 285, I think 3 times here. Go figure. Okay, so now partial derivatives you would have seen in Math, like here, Math 280, multivariable calculus. So these you're going to see all the time. And so here we have like a partial derivative of a function u with respect to x. So here u is assumed to be a function of x and other variables like y or t. But most frequently I'll be using this notation, just a subscript. So u subscript x is a partial derivative of u with respect to x. So that notation would have been used in Math 280, so I want to bring that back. So hopefully this is jogging your memory about certain things. Okay. Now, there's so many PDEs, but there's only a few that we're going to focus on in this class. Okay, so first we have what's known as the heat equation. So partial derivative of u with respect to t is equal to the Laplacian of u. Now, the Laplacian of u is a sum of second partial derivatives of u. Now, not all of the second partial derivatives, just the ones that are with respect to the same variable twice. So we have uxx plus uyy plus uzz. This is what we have in 3 dimensions. If this was only in 2 space dimensions, we would not have the uzz term. So however many variables you have in space, you're taking those second partial derivatives and adding them up. So that's the Laplacian. And it's often written this way as a delta followed by u. Now, here we have Laplacian expressed in Cartesian coordinates, the familiar x, y, z. But sometimes, like what if your PDE is defined on a circular domain? Then you would want to work in polar coordinates. Well, then the Laplacian changes. So if you work out the changes of variable from Cartesian coordinates to polar, then x and y to r and theta, then this is what the Laplacian looks like. And that's something that we'll deal with at the very end of the semester. Now, in the case of a heat equation, what does the solution mean? What does it signify? U refers to temperature. So U is a function of spatial variables like x, y, or x, y, and z, and time t. So it's the temperature of an object at a particular point in space at a particular time. But in general, you can also think of this as not just a heat equation. It's not just for modeling heat flow, but also just diffusion in general, any kind of diffusive process. In fact, so one example of that, which actually has come up in my research, is suppose you have, say, an image. And suppose the image is fuzzy. Well, fuzziness in an image is reflected in terms of fluctuation in the pixel values. You have at each point in the image a pixel value, or really 3 of them are referred to red, green, and blue intensities. So if those red, green, and blue values are fluctuating a little bit, there's oscillations in those values that visually shows up as fuzziness or noise. So if you think of the pixel values as a temperature profile, like an initial temperature profile, and feed that to this PDE as initial data, then what happens with heat energy? If left to its own devices, not influenced by an external source, it's going to smooth out. That eventually the temperature in a room, for instance, will converge to some kind of ambient temperature, like room temperature. So that's what happens with an image, that the color values will smooth out over time, thus removing the noise. So a lot of image enhancement is achieved, such as sharpening images or removing noise from images, by treating, by simulating a diffusive process. So there are a lot of situations that have nothing to do with heat energy, which this PDE is still useful. We'll also spend time on Laplace's equation, which is just Laplacian again, as before, just set equals 0. So there's no time in this case. This is only the solution U only depends on spatial variables. This is useful for modeling electrostatic potential. And we'll also spend time in a wave equation. So here we have a second derivative with respect to time. UTT is equal to Laplacian of U. So in the case of a one-dimensional wave equation, so UTT is equal to UXX, then what U refers to in this case is displacement of a vibrating string. So the height of a string, positive or negative, with respect to the x-axis, to show how the string oscillates over time. So all three of these equations will spend a good amount of time with. I want to comment about the Laplacian. So I mentioned how it's written this way, delta U. But here's another very common way of writing it that you should be aware of. Here we have this upside down triangle. It's a gradient symbol that you may remember from multivariable calculus. But here it's written as gradient squared U. Now, gradient squared by itself doesn't actually make sense. But the reason why it's written this way is that the Laplacian can be defined as the divergence of a gradient of U. Now, divergence is a concept that would come up in multivariable calculus, where if you take the gradient of U, that is a vector of first partial derivatives of U with respect to all your variables, so x, y, z. The way you take the divergence is you take these differentiation operators, partial derivative with respect to x, y, z, and you carry out what is called the dot product. That's what the dot here is for. Well, what is the dot product? That's something that comes up here anyway in Calculus 3, where you multiply, in a sense, corresponding components of vectors, and you add them all up. Well, here we're not literally multiplying. We're applying the differentiation operator to ux. So we have derivative of ux with respect to x would be uxx. Applying this to uy gives us uyy. Applying this to z gives us uzz. Something I was checking on is I'm moving my mouse across the screen. I can see that the mouse is moving here, but it seems to fall behind a little bit. That's annoying. So then you get uxx plus uyy plus uzz. So you add them all up, and we've seen from before that this is Laplacian. So Laplacian can be defined as a divergence of a gradient of U. And really, I'm just pointing this out to explain why it can be written this way as well as this way. I don't care which one you use, but textbooks tend to use both, so you should be aware of them. So our solution U, we refer to as a dependent variable. Whatever variables it depends on, those are the independent variables that are featured in the PDE, and we have partial derivatives with respect to those variables, x, y, z, t, or what we'll have in all of our examples. Most times we'll be dealing with just one space dimension, so your solution U would be a function of x and t. Are there any questions up to this point? I merely want to make sure that people are okay with any definitions or notation that I've used before we actually start making use of it. Okay, so why don't we bother with PDEs? The way the PDEs are often obtained, like how they're derived in the first place, including the ones I just mentioned, are from physical laws. So physical laws are often described in words, but then you can write equations that mirror those laws, and often these equations involve some kind of integral. But then through some manipulations, you can obtain the partial differential equation from that from a physical law, such as a conservation law, conservation of mass, conservation of energy. Pretty soon when we get into the heat equation, I will illustrate that process for you. I'll show you the derivation of a heat equation from a physical principle. And the derivatives that you see in these PDEs have certain physical interpretations, such as, of course, if U represents position, then you know that derivative of U with respect to time is velocity. Second derivative is acceleration, and so on. And so all of these kinds of terms come up in our PDEs. So why we care about solving them is that they help us understand how these physical processes play out. So if you have data that indicates, for example, a temperature profile, and you want to see what's going to happen to a temperature over time, then you're solving a heat equation. And maybe taking into account some other effects like external heat sources, etc. So you can model that. So what you learn from a behavior of a solution, you can take into account in real-world activities. So I'll give you a particularly important real-world example of this that actually relates to some of my own research. So before I came to USM, I was a faculty member for a brief time at Stanford, but not in the math department. It was in the Department of Petroleum Engineering. So in petroleum engineering, they make heavy use of PDEs. They're very interested in using PDEs to simulate, mathematically, the process of oil recovery. So my colleagues that I work with there, so what she was interested in are what are called gas injection processes, where CO2 is injected into reservoirs that have already been tapped out when it comes to conventional means of oil extraction, such as drilling or water flooding. After that is done, there's still a lot of oil there. Perhaps up to 85% of the oil is still there after doing those things. So when CO2 is injected in, you want to get an idea of what will happen in that particular reservoir. So they would gather all the data from a reservoir, all its properties, like what are the fractures and rock permeability and so forth. Those are coefficients within the PDE. They solve the PDE, and that gives them an idea of how the oil extraction process will go. How much oil can they expect to recover? How long do they think it will take? And they can take that data to management, who can then decide what to do with this information, as opposed to simply, let's drill here and see what happens. That's a very expensive decision to make. So the data that comes from simulations that involves solving PDEs helps guide those decisions, and so that they can make the best use of their resources. So that's just an example of how simulation using PDEs can be extremely helpful. Those kind of equations far beyond what we're going to see in this class. And now, my research actually specializes in what are called numerical methods for solving PDEs. We're not going to see that in this class. This class, you'll learn analytical methods for solving PDEs. So for certain PDEs like this, really the simplest kinds, it's possible to write down a formula for the solution. So your answers, like in your homework or test, will be, U of xt equals, you'll have some formula. But for PDEs that show up in real-world applications, that's generally not possible. And that's where numerical methods come in, and my research is about designing effective numerical methods, particularly in terms of efficiency. And even with state-of-the-art numerical methods, it takes energy companies like literally a month to solve one of these PDEs. The problem is that nasty. But what you learn about in this class are the building blocks for all of that. But simulation of processes like that is big business. It really helps big business. My research of late, because what I did there, that was several years ago, I worked with the acoustics group at the U.S. Naval Research Laboratory at Stennis. So we have a researcher who's, or a theoretician, who develops certain models related to one of the PDEs I showed you, the wave equation, so for modeling propagation of sound waves, for instance. And we looked at propagation of sound waves, for instance, in the ocean, or upwards through the atmosphere. And so I designed better numerical methods for solving wave equations that are much more complicated than this one. So those have, so those kind of simulations have applications, at least indirectly, for national defense. All right. So, how are we going to solve PDEs? So I mentioned we're going to be focusing on analytical methods as opposed to numerical. Well, numerical becomes grad student. As I mentioned, the first technique is called separation of variables, where the PDE depends on n independent variables. We break it down into that many ODEs, or possibly families of ODE or related ODEs. So we can fall back on techniques for solving these simpler equations to get solutions to the original PDE. Another approach is called integral transforms, such as a Fourier transform or Laplace transform. You would have seen the Laplace transform in a first ODE class. Here we'll deal with the certain Fourier transforms, where we can reduce the number of variables in the PDE. So for instance, you have a PDE that depends on two variables. Integral transform can eliminate one of them, so now it's reduced to an ODE. Eigenfunction expansion, which is actually related to separation of variables. We can determine that the solution is a linear combination of certain functions like sines or cosines, and then we figure out what that linear combination should be, often by solving ODEs. Okay, yes, I mentioned numerical methods. This class, Math 461, covers numerical methods for ODEs, and then graduate work builds on that for PDEs. But as I said, like this last point, we don't get into in this class. All right. Any questions up to this point? Yes.
Okay, so given any PDE, can you use any of the methods in finding the solution?
Okay, I'm sorry, I'm not sure if I answered the question.
So what I'm saying is, given any PDE,
And yeah.
can you use any of these methods to find the solution?
Oh, like these right here?
Yeah.
Unfortunately, what we'll find in this class is that these analytical methods are fairly limited. Like if you just have an arbitrary PDE, well, okay, here's an example. The kind of PDEs we'll deal with for separation of variables are ones that have constant coefficients. Well, what if those coefficients are not constant? Like say they're functions of x or functions of t. Then this cannot be applied. And generally the recourse in that case is to use numerical methods. There are some special cases where you can do something, but with analytical methods, things have to work out nicely in some sense. And even with those limitations, we'll still get to go pretty far. Like there are certain things we can do to transform problems in a way that makes them simpler so that we can use these techniques. But it's kind of like when you deal with in upper math classes. For example, okay, take calculus 2. All right, what do you learn there? Integrals. All right, you learn how to do quite a few different kinds of integrals using various techniques like integration by parts, substitution, partial fractions, etc. But even knowing all that, even after mastering all that, it'd be very easy for me to come up with an integral that you just would not be able to do. Like what you did in algebra, solving certain kinds of equations, it's still very easy to come up with equations that those algebraic techniques would not help you with. Now, it's easy to take my comment and interpret it as meaning that these are not useful, but they certainly are, because for more advanced techniques to deal with more elaborate PDEs, these are still building blocks. Or maybe there's some way to take a more complicated PDE and perform some approximation and still use these to get like a first approximation of a solution, and then somehow improve it from there. But yeah, like what we'll see when we deal with these techniques is, okay, PDE should be in a certain form, or there are some assumptions. That's a problem with math curricula. You get toy problems. But at the same time, like we're all just getting our feet wet anyway.
I feel like that's everything from after calculus too. Once you pass derivatives, everything is just there's no clean solutions for everything.
Yeah.
At least from what I've seen.
Yeah, like most of the time spent in this class will be on talk about certain ways of classifying PDEs. One is linear versus nonlinear. When it comes to nonlinear, there's not a whole lot you can do. We will see in certain cases you can. But at the same time, it's nonlinear ones that dominate the interesting application areas. That said, having worked with solving nonlinear PDEs, at least numerically, everything I've learned from solving linear PDEs has been useful. Like if you have a PDE that is nonlinear, you can linearize it, and then at least approximately solve it. And PDEs that occur like in the wild, I just realized that only those people who are here in the room can see my finger quotes. Sorry about that. There's a lot of uncertainty in those models anyway. Like the example I mentioned earlier about simulating an oil recovery operation. Everyone in that business knows that whatever results are produced, they're not going to be exact. You hope they're in the ballpark, but that's all you got. At least it's based on something. At least it is a data-driven solution. But you have to take into account there's a whole lot of uncertainty in that data. But at least you have something to go on. So in this class, whatever PDEs we have, we will come up with exact solutions for them. But for a more difficult PDE for which the exact solution is not known, there's really no point in pursuing that anyway, because there's a lot of uncertainty in the PDE to begin with. So there's really no such thing as an exact solution, just because the problem itself is not well defined. There's error in the problem. So certain properties of PDEs that guide your solution process is, for example, order. So the highest order derivative that appears in the PDE. So what would that mean, like for the examples I've shown you? These three PDEs, heat equation, Laplace's equation, and wave equation, all have either first or second derivatives with respect to some variable. So all of these PDEs are second order. And that's mostly what we'll deal with in this class. We'll also deal with certain PDEs that are first order. But there are PDEs of higher order. For example, the beam equation, which models displacement in beams for structure analysis. And then generally, of course, there should not be much displacement in a beam that's supporting a building, but there is some, and we have to understand it. It actually involves a fourth derivative with respect to a spatial variable. Okay, that's one property of a PDE. What is its order? Number of variables. How many variables does the solution depend on? Like I said, in most cases in this class, it'll be two. Spatial variable x and then time variable t. Or maybe for Laplace's equation, we'll mostly deal with two dimensions there, depending on two variables again, with polar coordinates, r and theta. Here's an important one, linearity. So if you have two solutions to a PDE, is a linear combination of them also a solution? This is something you would, the answer would be yes in the case of a linear PDE, at least if it's homogeneous, meaning there aren't any source terms. The three PDEs I showed you, heat equation, wave equation, Laplace equation, are all linear. If you have two solutions of one of those PDEs and you add them together, the sum is also a solution. Or a scalar multiple of the solution is also a solution. Here's another example of a linear equation that has a non-constant coefficient. So this is a heat equation, except I've given it a coefficient of x squared. So if I have two solutions of this equation, again, a linear combination would be a solution. So in spite of the fact that the coefficient itself is a nonlinear function of x, this is still a linear equation. But if a coefficient depends on the solution u, that's when we get into nonlinear territory. So here's a well-known PDE called Berger's equation, ut plus u times ux equals 0. So it's called a quasi-linear equation because it's almost linear in a sense, but because of this depending on u. So if this coefficient depended on only x or t, it'd still be linear, but dependence on u makes it nonlinear. Here we have u dx, the whole thing squared. So this is what's called a fully nonlinear PDE. So, because here we're taking a nonlinear function of derivatives. So whenever that happens, it's nonlinear. So that's the distinction between fully nonlinear and just quasi-linear. Here, we're not taking any nonlinear functions of the derivatives themselves, but the coefficients of those derivatives depend on the solution u. That's what makes it quasi-linear. But yeah, most of the time in this class, we're dealing with linear. Solutions of nonlinear PDEs can express some very interesting behavior, such as what are known as shocks. Traffic flow can be modeled using a nonlinear PDE, or actually quasi-linear PDE, such as this one. And the behavior, the unusual behavior you see in the solution, can actually corresponds to real-life behavior of traffic flow. And that's something that I'll explain when I get to that point in the class. So the math really does help explain what happens in the real world. Is the PDE homogeneous? Yes, if u equals 0 solves the PDE. So if I go, for instance, to the wave equation, Laplacian of 0 would certainly be 0. Second derivative of 0 with respect to time, of course, is 0. So the PDE is satisfied. So all three of these PDEs are homogeneous because 0 is a trivial solution. But by contrast, suppose I have Laplacian of u equals f, a function f, which is called Poisson's equation, a close relative of Laplace's equation. That equation is not homogeneous because u equals 0 would not satisfy it. Most times we'll have homogeneous PDEs, but occasionally you might deal with some kind of source term, which makes it non-homogeneous. Do your derivatives have coefficients? If so, are they constant coefficients, which is again, usually the case in this class, or variable coefficients, like this example here. Here's an example of a variable coefficient. And most of the time we'll spend on like second order linear equations that can all be written in this form. So some coefficient times times each of the second partial derivatives that you might have, and then plus coefficients times the first partial derivatives, and then plus coefficient times the solution u itself, and then you have some possible source term on the right-hand side. So second order linear equations can be written in this form. where the coefficients A, B, C, D, E, F are not necessarily constant, although in examples of interest, they usually will be. But for PDEs that fit this form, we can classify them into parabolic, hyperbolic, or elliptic, depending upon whether this expression is 0 for parabolic, positive for hyperbolic, or negative for elliptic. And the names, parabolic, hyperbolic, or elliptic, don't really correspond to the behavior of a solution of the PDE, but just the sign of this discriminant here. But PDEs that are parabolic, hyperbolic, or elliptic behave very differently from each other. And that's why we have this classification system. So, and each one of the PDEs that we'll spend the most time on in this class are one of the three types. So the heat equation is parabolic, wave equation is hyperbolic, and the Laplace is elliptic. So to give you an example of how different they are, we have a hyperbolic equation that is used to model what is called advection or propagation. You have something moving, like a wave, moving at a finite speed. And the coefficient of uxx in the wave equation indicates what the speed is. And whereas the heat equation being parabolic, suppose that your initial data, your initial temperature profile is 0 everywhere except in one small region. Then once time moves forward, even the least little bit, the solution will become non-zero everywhere. So, in other words, you have what is called infinite speed of propagation, that the non-zero content of initial data influences the solution throughout your spatial domain at an arbitrarily small time, which does not happen with hyperbolic equations. So, heat equation, you have change happening infinitely fast. Wave equation happens at a finite rate. So one of the first homework problems is, given some PDEs, classify them according to these categories given here. Because when you come across a PDE, these are things that you want to know about it right off the bat before you think about how you might solve it. So that might indicate which approach that you want to take. So that's why this kind of classification is important. Check the chat here. Okay. So are there questions?
Why is the quadratic, the discriminant of a quadratic equation used for that, the second order linear equation?
So what happens is, when you try to solve a general PDE such as this one, what you want to try to, what you can do is, and this is something I will see later on, is first try to simplify it. You want to, like for example, reduce the number of terms that have second partial derivatives in them. For example, the hyperbolic equation can always be written in a form where these terms of A and C go away. You'll have a B term and then possibly lower terms. And the process of transforming it into some kind of canonical form, how that process goes depends on the sign of this. So what happens is, if you're trying to come up with solutions for these kind of equations, that kind of simplification and solution process breaks down very differently depending on whether a certain quadratic equation involving, really the quadratic equation coming from this, has 0, 1, or 2 solutions. Question there. Other questions? Now, okay, so the first homework assignment, I've only talked about lesson 1 today, comes from, so those are the first few problems, but the other 3 lessons are fairly short, and that's what I'll be covering in the next class on Monday. So after that is when you'll have enough information to do the entire first homework. And it's yeah, you'll have a good amount of time to do it. Like I said, we're trying to ease into things. And then after that, when I get into lesson 5, these are the lessons in the textbook. So we get into actual solution algorithms. But we spend some time here on how do we formulate problems, because really when you're solving a PDE, it's not just a PDE by itself. There's other pieces to the problem that help narrow down to unique solutions, such as boundary conditions or an initial condition, and how do we come up with the right ones for whatever situation is in we're in. Okay, so. So one of the things that can be kind of strange about this class is that what you tend to think of as ordinary math problems, we don't really get into that much until after really more like the second homework. So we're just, like I said, we're just kind of getting our feet wet here. But that sometimes throws students off, that it's different sort of problems they're expecting. Okay, so that's something to keep in mind. Okay. And because as usual, what happens with these classes, class tends to be a quiet bunch. Although at least you had a few questions today, so that's actually better than usual from what I see. But what I'll do is I've covered everything I need to cover. And what I'll do is I'll end the recording at this point, but since I have to be here for the next class period anyway, I can certainly stick around in case anyone here in the room or any of you who are online have questions. But otherwise, I can wrap up. This will be posted in Canvas later.